Okay, welcome back, everybody. I'm really excited today because one of the big concepts of analysis is we're going to discuss today, and that's the concept of compactness. Now, compactness is a concept that when I first learned about it, it just seemed to me rather unmotivated and perhaps not. It wasn't clear for actually many weeks why we even cared about this concept. So I hope to teach you differently and maybe give you some sense of why this concept is important before we actually make the definition. So what have we been doing so far in this course? Well, we've been doing a lot of things, but I would say one of the big themes running through the material we've covered so far is this idea that when we're dealing with the analysis of the real numbers, we are wrestling with the infinite. Okay? We are, yes, music please. We are wrestling with the infinite. In what way are we wrestling with the infinite? You want to give me some examples from our last few weeks here? What way? Yes, Katie.
We have sets of numbers of which there are infinite numbers of numbers.
Okay, so for instance, the real numbers form an infinite set. Yes, and that was a little bit problematic at first because we had this idea that, once we started with, even the integers are infinite, right? But once we started defining other concepts such as fractions, we had to deal with the infinite pairs of numerators and denominators, right? And then we had this idea that there are gaps still, right? And we wanted to fill them in somehow, right? That's really wrestling with the infinite. Okay, what are some other ways in which we wrestle with the infinite? Well, we had this idea that somehow there are bigger sets, that the real numbers are somehow larger than the rationals, right? So countable and uncountable infinite sets. Later on, we're going to start talking about functions, okay? Functions, in particular, you think about functions in calculus, you graph them, right? You're usually dealing with things like continuous functions. Well, what does it mean for a function to be continuous? That's really wrestling with the infinite, right? Because if I had a function on a finite set, that'd be rather boring, right? You don't have to talk about the relationship between a value of a function at this point and the value of the function at this point, right? A function on a three-point set is just a three-dimensional vector, isn't it? Right? You put a number here, you put a number here, you put a number here. Okay, rather uninteresting from the point of view of analysis. We're going to start filling in the gaps later with continuous functions. Okay, so we are wrestling with the infinite in this course. And the other, of course, theme that I want to hammer home, if it hasn't already begun to show itself, is that finite sets are nice. Okay, why are finite sets nice? Well, they're small. That's one thing. Okay, there's only finitely many things. They're small. Can't say it any better way than that. Okay, of course, the associated concept here is boundedness, which we will talk about. What's another reason finite sets are nice? Well, they're closed sets. In fact, they're trivially closed. A closed set is a set that contains all its limit points, and finite sets have no limit points. Okay, so they clearly contain their limit points. This will become apparent why we care about this soon. In the metric space that's the real numbers, the finite sets actually contain their supremum, right? That's one of the things you showed on your homework exercise from a couple weeks ago. And if they contain their supremum, then we can rightfully talk about a maximum or a minimum, right? You give me a set of finite numbers, I can say there's a maximum and a minimum. What I mean is there is a supremum and it's in the set. Yes? With me? Okay, and one other reason we care about finite sets is that whenever you do anything with finite sets, the process terminates. Okay, so if I say I'm going to do something on a finite set, I know that there will be an end, that this process will end. Okay, so these are all great reasons why we care about finite sets and why they're nice. but we're wrestling with the infinite in this course. Okay, so the concept of compactness is really about finiteness. In particular, if you have a set that is compact, it is, this is the way I like to think about it, it is the next best thing to being finite. Okay? It's the next best thing. Now, when I make this definition, it's not going to be apparent why any of these things are true about compact sets, but they are. Okay? So each of the things I've just mentioned about finite sets are also things that are true about compact sets. As the name suggests, compact sets are compact, right? Which is sort of a way of saying that they're small in some sense. Okay. Okay, very good. So let's make some definitions. Let me erase some of the scratch work here that remains. Make some definitions, and then we'll see why this is a important concept. So the first thing we have to do is we have to talk about what it means to cover a set. So here's the definition. So what do you think? I'm going to make a definition of an open cover of a set. And as the name suggests, what do you think I might mean by the words open cover? Open cover of a set. Okay, that might be a little more complicated definition than we want. So an open cover is just going to be a collection of open sets that cover a particular set. Okay, so here is let's call this set E. This is living in some X. Okay, X is always a metric space from now on. An open cover of some set, whatever it is, E in X is a collection of sets, of open sets, if it's an open cover. It is a collection of open sets, which I'll denote, let's say, G sub alpha, whose union covers, if you don't like the term covers, a more mathematical term would be contains E. Okay, and this is all living in some metric space X. Okay, so maybe I should put this in your notes so that it gets there. I'm just going to say from now on, X is always a metric space. Whenever I use the letter X, I mean, I imagine it's endowed with some metric. Okay, so a picture might be something like the following. Let me grab my colored chalk here. So here is some set E, and I have a bunch of open sets, which, okay, usually you dot open sets, dot the boundaries, but that's hard to draw a lot of. And so the way, another way to sort of notate an open set is to kind of draw it curly, okay? So you just imagine these are the open sets whose union contains all of E. So is this a cover of E? No, I've missed some points. Yes? So maybe I'll throw in one. There is an open cover. Okay. Okay, so any questions about the definition of an open cover? I should mention that sometimes we just say the word cover because we're never going to talk about any other kind of cover. Okay? Okay. And while we're at it, let me actually put another definition